The transaction handling capabilities of BizTalk orchestrations offer yet another compelling reason to use them for integrating your systems. This is the kind of stuff that's really hard to get right. We walked through that simple purchasing scenario in Module 8. Even in that simple business process, we saw that it could get pretty complicated when we had to start thinking about everything that could go wrong. And then we had to figure out what to do to back out the processing that had completed so far. And we really didn't even talk much about what it would take to implement that. Of course, it's possible to write custom code to implement the type of transaction handling that orchestrations offer. The question is, when that's all done, how much did it cost? What kind of reporting and tracking capabilities does it include? And is it going to be easy to reuse that in other integration scenarios? But before we go any further, let's take a look at what we need to know to implement transactions in orchestrations. In this module, we'll start off by talking about transactions at the conceptual level. And in that discussion, we'll take another look at how the orchestration runtime makes use of persistence and how that persistence behavior allows the orchestration runtime to handle transactions. Then after the conceptual discussion, we'll take a look at what we need to know to implement transactions in our orchestrations. So as we start looking at things from a conceptual point of view, we need to consider a couple of questions right up front. First of all, what are we talking about when we say the word transaction, particularly when we're talking about transactions in the context of a BizTalk orchestration? What exactly does that mean? And then what about this thing called persistence? What exactly is orchestration persistence and how does it help us? And a follow-up to that is, well, when does an orchestration go about doing this persistence? Once we understand the answers to those questions, we can start thinking about how we can apply transaction handling to our own orchestrations. The first question to answer here is, what is a transaction? What are we talking about? Well, we could talk about the ACID characteristics of a database transaction. A transaction needs to be atomic, it's all or nothing. It needs to be consistent, it needs to leave the database in a consistent state, so all of the data is valid. It needs to be isolated, so it can't interfere with other transactions. It needs no knowledge of the other transactions being executed around it. And it needs to be durable so that if there is a failure at any point, there has been no data loss. We know everything that we need to know about this particular transaction to roll back and clean up. So those characteristics allow us to rely heavily on the integrity of a database system. To some degree, those characteristics apply to the transactions we're talking about here, but we need to think in more general terms because we're talking about transactional business processes. What does a transaction mean in terms of a business process? Well, we obviously can't hold a database connection open for a week while we wait for a sales order to complete. And then when our ordering process needs to communicate with other systems to get the job done, we can't hold open connections to those systems as well, so we can't really rely on something like the distributed transaction coordinator to help us much here. Well then, how can we talk about transactions if we're talking about operations that are going to take days or weeks to complete? Well, you could think of it this way. These business process transactions are design patterns. They provide us with a conceptual framework for thinking about what needs to happen if a business process is canceled midway through, or if we encounter a hardware failure somewhere along the line and we need to recover, keeping the business process on track all the while. Business process transactions also give us a way to organize the procedures that need to be performed to clean up a failed business process. Of course, we do need to think about the cleanup process as a whole, but the transaction model ultimately lets us break that down into manageable pieces. And that becomes particularly important when we need to start implementing these things. And even more important when we need to start explaining this process to someone else. So while there are some similarities to database transactions, and database transactions do play a role in all of this, we need to expand our notion of a transaction at this level. So let's think about two different types of transactions, atomic transactions and long-running transactions. Atomic transactions are most similar to a database transaction, and in some cases that's exactly what they turn out to be. All of the operations in an atomic transaction are going to succeed or fail as a whole. The characteristic of consistency is a little more difficult here because we may be talking to three different systems and they may not all be database systems. And we may not know what kind of validation those various systems are doing. So if all of our operations within an atomic transaction are interactions with the database, we can probably say consistency is a safe bet. But if in one case, if we're sending an email somewhere and then another of the operations is to send a message to a message queue, and we also write to a database, well, we don't know exactly what kind of consistency we're talking about there. I think it's pretty safe to say there won't be any sort of consistency check on the behalf of the email. And thinking about it in terms of isolation, well, that's a difficult one too. Again, if all of the operations are taking place through interactions with a database, yeah, we can probably assume that isolation will be upheld in that transaction. On the other hand, when we start communicating with multiple systems again, we really have no control over isolation levels in that case. Well, what about durability? Well, durability is something we should be able to count on. Yeah, we may not be able to rely on one of the systems that we're interacting with to maintain durability, but we know that we can rely on BizTalk to maintain all of the information about our business process. So in short, when we talk about atomic transactions in this context, we're talking about short sequences of operations that will succeed or fail as a whole. Well, what do we do about the fact then that our orchestrations can run for a long time? How do we handle that? Well, that's where long-running transactions come into the picture. Long-running transactions are designed to run for days or weeks or months, and yet retain the ability to undo and clean up a business process that has been aborted or canceled somewhere along the line. So unlike an atomic transaction where everything is committed all at once, to implement a long-running transaction, we need to save the state of our business process at various points along the way. And of course, those points need to be well defined for all of this to work out in the end. All right, well, that's all well and good, but how does that relate to orchestrations? Well, you have worked with the scope shape in the past, and we have talked about the scope shape's exception handling capability, and I've mentioned the scope shape's transaction handling capability as well. By making use of the scope shape in our orchestrations, we can break down our business processes into manageable chunks. So a scope shape offers a framework for implementing these transactions. And it helps us out in a couple of ways. Within a scope shape, we can specify a sequence of operations that need to take place in order to complete some particular business function in our process. Then, the scope shape allows us to add a set of shapes to define what needs to happen if something goes wrong, and that is our exception handler. And then by taking advantage of the other feature that the scope shape offers, we can add a compensation block. And then within the compensation block, we can specify the sequence of actions that need to be taken to undo the particular business function defined by the scope shape. We can actually take control over exactly what compensation blocks should be executed if a particular failure occurs. For example, in the event that the employee who placed the order cancels it, we want to roll that back all the way to the beginning. We'll probably archive things off, and those will very likely be the compensation steps that we define. And then that purchase order would be marked as canceled in the purchasing system. On the other hand, if our vendor comes back and indicates that they cannot deliver the entire order all at once, and they can only give us 3/4 of the material, in that event, we really don't want to roll back all the way to the beginning of the purchase order. We just want to go back to the point where we chose which vendor should fulfill this order. In some cases, maybe the default compensation behavior that BizTalk provides takes care of the need. It will go back and execute the compensation block of every scope shape that it contains. If not, then we can go and for each particular type of failure or cancellation, we can specify exactly which compensation blocks should execute to clean up the process. So the scope shape really can help us out in a lot of ways. It can help us out at a conceptual level, just thinking about all of the considerations that we face when we're thinking about these business process transactions. And it actually helps us implement those. And ultimately, it actually compiles into code. I showed you an animation in Module 8 that described how the orchestration engine will serialize an instance of an orchestration to the database if it doesn't have any work to do, so that it can free up those memory resources for another orchestration to get work done. And that process was known as dehydration. And then once a message came in for the dehydrated orchestration to process, the orchestration engine would rehydrate that instance and let it get its work done. So that's one example of orchestration persistence. There are actually other times at which the orchestration engine will persist an instance to the database as well. And that actually is at the core of the orchestration engine's behavior. It watches rather vigilantly for changes to the state of an orchestration instance, and it does the best that it can to capture the changes to that state before anything bad can happen. And so that helps us out in a few different ways. Obviously, it's going to make better use of the resources that are available, but also it provides failover capability. So if an orchestration had been executing and each step along the way, its state changes were persisted to the message box, and then the server on which it's running crashes, the orchestration engine has everything it needs to reinstantiate that orchestration on another server and let it continue processing. It also provides the ability for a BizTalk group to handle a controlled shutdown cleanly. So if for whatever reason the BizTalk group had to be taken offline, all of the orchestration instances that were currently in process would be serialized off to the database, and then when BizTalk came back up, all of those orchestrations would be able to pick up where they left off. Now, of particular importance to us in this discussion is that it's this persistence behavior that provides the support for the types of transactions that we're talking about. So let's dig into this a little bit deeper and get an understanding of the points at which the orchestration engine is going to go about and do this persistence. So here we have a list of persistence points. And quite frankly, this persistence behavior cuts both ways. On the one hand, it serves as the basis for this transaction capability we're talking about. But on the other hand, excessive persistence of an orchestration can lead to noticeable latency. So it's a very good idea to keep this list of persistence points in mind as you are developing orchestrations. Okay, with that out of the way, let's take a look at this list. First on the list is when a message is sent within a non-atomic scope. So in this case, we have some data being sent out through a send port, and so the orchestration engine needs to have the state of the orchestration at the point at which it produced that message. Otherwise, it could be sending out a message that it could never reproduce. Notice, by the way, that this point specifically states that this applies when messages are sent within a non-atomic scope. Then next on the list is that an orchestration will be persisted as a transactional scope completes. And that's true for scopes marked as atomic transactions and scopes marked as long-running transactions. The difference here is that the atomic scope will not be persisted until the end of the scope. So there's the key difference between the two types of transactions. So implied in that is if you have one or more send shapes within an atomic scope, that message will not actually be sent until the end of the atomic scope. Nothing will be committed to the message box, including the state of the orchestration or any messages that are sent until the atomic scope completes. On the other hand, a long-running scope can be persisted at many points within its lifetime, and then it will also be persisted as the long-running scope completes. So one other point to take away from this is that you don't want to mark a scope as transactional unless you really need that transactional behavior. Otherwise, you're just paying the price of one more persistence point, and it may not be helping you. Another point at which an orchestration will be persisted is if it hits a start orchestration shape. And that makes sense because this is a lot like sending a message out through a send port. When an instance hits the start orchestration shape, it's going to be sending a set of variables, and quite likely some of those will be messages to the new orchestration. And so if anything were to fail while attempting to start up that new orchestration, the orchestration engine would need to be able to back up to the last known state of the caller. Next on the list is debug breakpoint, and that makes sense. The orchestration, of course, could be sitting there waiting for quite a while before someone fires up the orchestration debugger and steps through it. And so rather than run the risk of losing any data in the meantime, the orchestration engine is going to persist that. And then after that, another persistence point is dehydration. And we're familiar with that concept at this point. And there isn't necessarily all that much we can do if we're waiting for some sort of a response. Dehydration is a good thing. It allows the orchestration runtime to make the best use of the resources that it has available. We have some ability to tune the dehydration behavior. We could set some threshold times in the administration console, but for the most part we really have to leave dehydration up to the discretion of the orchestration engine. And then an orchestration will be persisted as it completes, so that the engine will have a record of its final state, And of course, an orchestration needs to be persisted if the system is shutting down. And that would be in the event of a controlled shutdown. So there are a couple of other points worthy of mention here. One is this issue of serializable variables. Now, when I introduced the scope shape in Module 8, I mentioned that if you absolutely have to use an instance of a class that is not marked serializable, there is a way to do it. And you do that by simply declaring that variable within a scope that is marked as an atomic transaction. Since the orchestration will never try to serialize during an atomic transaction, the orchestration compiler won't flag that as an error. If you need to call one of your own classes, and you have the option of implementing static methods on your class, by taking that route, you don't need to hold on to a reference to an object. You can just call those static methods directly. The second point that I wanted to mention is that you will probably want to minimize the amount of state that your orchestration is holding on to at any particular point, particularly if the messages that you're working with are large or the collections of variables that you're working with are large. Because we certainly have something to gain from this persistence behavior, but if you can minimize the price that you have to pay for it, that will only work in your favor down the road. One thing you can do in that regard is, of course, to be judicious in your use of scope shapes. It's perfectly fine to use scope shapes that are marked non-transactional. So again, only configure a scope shape with a transaction type if you absolutely need that transaction behavior. Otherwise, leave it non-transactional. Just like you can declare variables within a block of code in other programming languages, you can declare variables within a scope, and when that scope completes, the orchestration engine doesn't have to worry about those variables. They're already persisted, and it is only concerned with the variables that are currently in scope. Now, for the most part, you probably don't have to worry about that so much. But if your orchestration is going to be processing large messages and you know it will be under heavy load, it's something worth thinking about up front. When you're ready to implement a transaction in your orchestration, you will need to add a scope shape in the orchestration designer. And you'll need to specify the type of transaction for that scope, and that's something you want to think carefully about. In particular, if you find yourself marking a lot of your scopes with transactions, you might want to find a way to minimize that number. If you can avoid the transaction, you can avoid a persistence point. Then you'll need to determine if the scope shape requires any sort of compensation. Is this something within the business process that will need to be undone later? And of course, as developers, we need to always think about errors, so you'll want to identify any errors that might occur within the scope and how you can handle those. And then use that information to implement one or more exception handlers. And then based on your business requirements, you can define whatever compensation code is required to undo. And maybe it's as simple as sending an email to someone to notify them that the order was canceled. But it very well could involve contacting multiple systems and making an update to each of them to keep them apprised of the situation. Now let's shift our attention to the particulars of what we need to do to set these things up in the orchestration designer. So far, whenever I've mentioned an orchestration transaction, I've mentioned a scope shape to go along with it. Well, it is possible to set a transaction type on the orchestration itself. And you'll actually have to do that. As soon as you set a transaction type on a scope shape within your orchestration, you will need to set a transaction type on the orchestration itself as well. Now, there are some nesting rules involved. A scope marked as an atomic transaction cannot contain any other transactional scopes. It can contain other scopes, but not any other transactional scopes. A scope running as a long-running transaction can contain other transactional scopes. It can contain nested long-running transactional scopes, and it can contain atomic scopes. So if you're going to mark any of the scopes within your orchestration as transactional, make sure you mark your orchestration as transactional. Otherwise, you'll get flagged with a compiler error. And if you set the orchestration transaction type to atomic, don't bother trying to nest any transactional scopes within it. You will still be able to add scope shapes within your orchestration, you just won't be able to mark any of them as transactional. Notice in this screenshot of the properties window for an orchestration that if you mark a orchestration as transactional, one of the new properties that is added to your orchestration is the compensation property. The default behavior of an orchestration's compensation is to simply execute the compensation block of each of its child scope shapes. If, on the other hand, you want to take explicit control over that compensation process, you can change that property and you will get a second page in the orchestration designer that will allow you to start adding shapes to define exactly what needs to happen if compensation needs to execute for this orchestration as a whole. Here's a summary of what we know about long-running transactions. They are meant to handle long-term transactional behavior. A long-running transaction may encompass behavior that extends over weeks or months. And so we really can't think about them in terms of an ACID transaction. We simply rely on the orchestration engine to retain the state of the business process at each point along the way. And then actions within a long-running transaction are always subject to compensation until the actual long-running transaction completes. And finally, long-running transactions allow for nesting. So they can contain other child long-running transactions, each with their own compensation blocks. And they can also contain atomic scopes, which of course can have their own compensation blocks as well. And then of course we've been talking about atomic transactions, which are more akin to the database transactions that we're familiar with. The points on this slide really pertain to the interaction between the orchestration engine and the BizTalk message box. They do not strictly pertain to the orchestration as a business process, to all of the systems with which it is interacting. So, that being said, the actions taken within an atomic scope will all be written to the message box together as a single transaction. So if you have a scope that performs an operation and then sends a message, and then performs another operation and then sends a message, and then calls a .NET class and then sends a message, those messages will not actually be written to the message box until execution reaches the end of that atomic scope successfully. Now, the transaction that's initialized in an atomic scope does not flow out past the message box. So the physical send ports that actually transmit these messages are not going to participate in the transaction that was initiated by the atomic scope. Having said that, it is possible to use an atomic scope shape to initiate a distributed transaction that's governed by the Microsoft Distributed Transaction Coordinator service. And you do that by calling components that are derived from the system.enterpriseservices.serviceComponents class. That's the base class for components that can support these types of transactions. And then you will need to set the isolation level on your atomic scope to match the isolation level of those DTC components. And if you get that all set up correctly, your atomic scope actually can participate in an ACID transaction. And then with all of those pieces in place, you can go ahead and make a call to one of the DTC components and then call another of the DTC components. And then the MSDTC can instruct the components when they should commit. Probably the two most popular uses for an atomic scope are to make use of a class that is not serializable and to minimize persistence points in certain cases. Now just be careful with that. Just marking your scopes as atomic scopes doesn't necessarily mean that performance is going to improve in the long run. After all, you're preventing the orchestration engine from the job that it's trying to do. It's trying to manage system resources, and we more or less tie its hands if we start marking every scope as atomic. One last point that I'd like to mention is that you will find that you cannot define an exception handler for an atomic scope. And that's because the exception handling is implied. If anything fails within the atomic scope, all of the changes should be rolled back. So it more or less provides automatic exception handling. We've seen this slide before, so it's just here as a reminder of the two different types of invoking an orchestration. So the call orchestration shape, as depicted on the left, is a synchronous call. It actually is a function call from one orchestration to another. So in this case, the variables do not actually pass through the message box, and so there's no persistence point that's required. The start orchestration shape, on the other hand, is going to invoke an asynchronous call to another orchestration. and those variables will be passed through the message box. And so we do have to pay the price of a persistence point in that case. In this demonstration, I will show you how to add a scope shape to your orchestration and how to configure it with a transaction type. And of course, in order to do that, we need to configure the orchestration with a transaction type. Once we have that set up, I will show you how to add an exception handler. This orchestration will look similar to the orchestration that you work with in the lab, but it's just a little bit different to highlight some of the behavior of the transactional scopes. I'm going to start off this demo by opening the process order credit orchestration. So this orchestration should look familiar to you by now. We accept a sales order and then send a loan to the bank. I'm going to set the transaction type on this orchestration, but I'm going to intentionally break the scope and transaction nesting rules. So I'll start by setting the transaction type of the orchestration to atomic. And then give this transaction identifier a name. Okay, now the next thing I'd like to do is add a scope within the orchestration and then try to set its transaction type, and you'll see what the error message looks like if you were to ever break the transaction nesting rules. So I'll add the scope shape here. And this will be our send to lender scope. And now I'll set the transaction type to long running. Okay, so we see the error box and the detail indicates that we cannot set a transaction on this scope because it is already within an atomic transaction. Okay, well, let's correct this by setting the transaction type on the orchestration to long running. And now I can go back to this inner scope and set its transaction type without an error. Now I'll move the shape, the decide shape that handles the send to the lender. All right, now that we have a scope shape in our orchestration, we can implement an exception handler. I can add an exception handler to this scope shape by right-clicking and then choose exception handler. Okay, first, let's configure the properties on the exception block. We can give it a name and configure it with an exception object. So for the exception object, we need to give it a name as well as an exception type. Now, the bank notification send port is configured to provide a delivery notification. So if the physical send port actually fails to transmit that message to the bank, then the orchestration will receive an exception. And the BizTalk orchestration runtime defines an exception specifically for delivery failures. So let's find that in the list. There we have delivery failure exception. And now, when this exception handler is executed, we will have a reference named EX, which will give us access to the delivery failure exception object. Okay, well, what can we do with that information? In this case, I am going to take a copy of the sales order message and update the comment with the error information that we get back from the exception object. So I'll construct a new message using a message assignment shape. And we will be constructing the message cancel order. And then within the message assignment shape, we can add the code to make a copy of the sales order message, and then add another line to format the comment string. So we will report that the order was canceled and the delivery of the loan document failed, and then also provide some detail that we received from the exception object. We'll report the ex.message string. Okay. Now I'd like to send this message out to the cancel order send port. So we'll need a send shape to do that. And then I need to configure that. And this will send the cancel order message. And then I just need to connect it to the cancel order send port. Then I'd also like to terminate this orchestration if this exception occurs. That way it will show up in the BizTalk administration console. And then someone would be able to investigate and find out why these messages are not being transmitted to the bank successfully. And finally, to complete the implementation of a long-running transaction, we need to define the compensation code. So the particulars of the compensation code are going to be totally dependent, of course, on the business process that you're automating. So you'll need to understand exactly what each system involved in this business process requires in order to undo the actions that had previously been completed by this scope. And if there is some step that just can't be automated, you can always send a notification to a person via email, perhaps. And so if compensation is going to execute, a parent scope will call the compensation blocks on its child scopes, and those individual child scopes will call the compensations on their own children, and so forth. And each scope, it gets to determine exactly how the compensation blocks are called on its children. Maybe one scope just needs to always call every compensation block on its child scopes. Others might need to pick and choose depending on the circumstances. The default compensation behavior is simply to call the compensation block of each child scope. And in the case of nested scopes, if you do not define a compensation block on a scope that has children, the default behavior is that the compensation blocks of each of the child scopes will execute. In this demonstration, I'll show you how to add a compensation block to a transactional scope shape. And then in order to trigger that compensation block, the orchestration will need to throw an exception. So I will add a throw exception shape to simulate the event of a customer canceling the order. And while that might not seem like something that should trigger an exception, we actually need to implement it that way. The only way to initiate compensation is within an exception handler. So I'll add that throw exception shape, and then what would happen at runtime is the orchestration's default exception handler would catch that exception, and since this orchestration is configured as a long-running transaction, the exception handler would call the orchestration's default compensation code, which would in turn call the compensation block on the send to lender scope shape. Once we have everything set up, I'll walk through the execution sequence, both the sequence that would trigger the exception block to execute, as well as the sequence that would trigger the compensation block to execute. Alright, so here we are back in the process order credit orchestration, and this time let's add the compensation block. So we can do that by right-clicking on the Send Loan to Sender, and then choosing New Compensation Block. Okay, there we have it. Now let's right-click on that and set the properties. Okay, now we can add shapes. And this compensation block is simply going to report that the order has been canceled. So let's add a construct message shape and then a send shape. And this too will construct the cancel order message. But it will just provide a different value for the comment. So make a copy of the sales order and then set the comment. And now we can insert the send shape. And send the cancel order message out. Okay, so now that we have all of these pieces in place, let's walk through the process of a message passing through and triggering an exception. So the message will arrive on the receive shape and then be passed to the loan. And then the map will construct a new loan message. And a complete sales order message will be sent out. And then the determine lender decide shape will send the message out to the bank, but that delivery to the bank will fail. And so now that exception will be thrown and caught by the delivery failure exception handler, which will then construct a cancel order message and send that out. And then the orchestration will terminate, and that will be suspended, non-resumable in the BizTalk Group Hub. Okay, now let's rerun the scenario and see what happens when we use compensation. So we receive the message in the receive shape, construct a new sales order complete, and send that out. This time, however, we're going to handle this with internal credit. It's not going to be sent to the bank, so execution passes down the other branch. And then everything succeeds until we get to the very end, and now this is where the customer is going to cancel. And so this shape is throwing an exception. And so the default exception handling of the orchestration is going to kick in and call compensation on these inner blocks. Okay, so that means that our compensation block will start to execute, and that will construct a new cancel message and send that out to the send port. Okay. So you can see that the exception block executed when the error occurred inside the scope, and then the compensation block executed when the error occurred after the scope was complete. In this lab, you'll have a chance to create an orchestration that implements an exception handler as well as a compensation block. Just be aware that the orchestration that you will create here is similar to the one that you saw in the demos, but it is not identical.